In this video, I'm going to go over two special right triangle scenarios that might occur. We're going to start with the 45, 45, 90 special right triangles and then move into the 30, 60, 90. So starting with the 45 degree, and 90 degree right triangle, right? And we did a CLT like this in class that would help us kind of walk through how we got all of these different ratios for the relationship between the sides. But we know this is a right angle. We know this angle is 45 degrees. This one is also 45 degrees. And so the way that you need to memorize this, or at least I think you'll practice enough that you will memorize it, is that we have the side lengths that are opposite the 45 degree angles are the same, which makes sense. And then the side that is across from the 90 degree angle, the hypotenuse, is going to be that value times the square root of 2. Allie, shh. Sorry about that. Okay, let's move into 30, 60, 90. Now, this is going to be another one that we have proved in class already. So I'm just kind of putting on these notes what we've already talked about in class. I'm going to draw another right triangle. All right, so you know this is a right angle. All right, I'm going to draw my 30 degree angle here. It doesn't matter, you could draw it in either spot. All right, the other one is 60. So across from the 30 degree angle is going to be our smallest side length. So I'm going to use that as side length A. If you look at the hypotenuse compared to that smallest side, it's going to be twice that length. And then the side that's across from the 60 degree angle is going to be that smallest side length times the square root of 3. Okay? So again, we're going to use these two kind of special right triangles to help us with some questions. All right? Okay, let's move forward with these. So we're going to solve in these first four to find the missing sides of each triangle. Again, we're going to use, you can notice all four of them are either 45, 45, 90 or 30, 60, 90. And if necessary, since we're not using a calculator, we're going to use radicals in our answer. We're going to be okay with radicals. All right. So this first one, we know if that is 45, this is also 45. You'll notice the side length for one of those is given, which is 7. And referring back to our notes up here, right, for 45, 45, 90, you'll notice that the side lengths are the same. So T is going to be equal to 7. For the hypotenuse of R, that's going to be equal to 7 times the square root of 2, right? Refer to your notes if you need to. All right, so that's it for the first one. Let's do number 2. So these are 30, 60, 90. They're giving us the 30 degree angle side right across from that. So I go to the hypotenuse first, right? The hypotenuse over here is going to be double that, or 8. And the side length that is across from the 60 degree angle is your smallest side times the square root of 3. Okay? Number 3, very similar. They've given us that 3 again, or I should say they've given us the side length that is across from the 30 degrees, the smallest one. So the hypotenuse is going to be double that, which is 6, and F is going to be 3 times the square root of 3. And the last one on this page, number 4, they're giving us the side length across from the 60 degree angle. So I'm going to find this small side first by taking that side of 15 root 3 and dividing it by the square root of 3, right? Go back to your notes, right? They gave us this one here. I'm trying to find that one. So I'm going to divide by that square root of 3. Those are going to cross out and leave me with just 15. All right, so that means the hypotenuse is going to be double that smallest side of 15 to be 30 units. Okay, so that's kind of the most basic way you'll use these special right triangles. Okay, let's flip the page. All right, so keep going here. They're telling us in number 5 that these side lengths are the same, this isosceles right triangle. So we know that these have to be 45 degrees if they're going to be the same length. And they're giving us the hypotenuse. So to find the smaller sides, I'm going to take the hypotenuse and divide by that square root of 2. You'll notice it crosses out again. So R is 6 and T is also 6. Go to number 6. All right, they're giving us the hypotenuse this time. So I'm going to find Y first, since that is across from my 30 degree angle, which is half the hypotenuse. So 12 divided by 2 is 6. This 60 degree angle across from that is X, which is going to be my small angle times the square root of 3. Let's go to 7. Number 7, they're giving us across from the 60-degree angle. So I'm going to find k first, that smallest one, by doing my 5 root 3 divided by the square root of 3, which would be k is 5. And then finding the hypotenuse, I'm going to double that smallest one, right? The one that's across from 30 degrees to get y is 10. Okay, number 8. They're giving you notation that says that these angles are the same, so they're 45 degrees. They're giving you the hypotenuse. So I'm going to take that 11 root 2 and divide by square root of 2 to find that these sides are both 11 units. Number 9, very similar to, I think, number 5. They're telling us those are the same. So I'm going to use 45 degrees here. They're giving us the side length, not the hypotenuse. So the other leg is going to be 9. And then the hypotenuse, which is t, is 9 root 2. Again, I know I'm going pretty quickly on these, but once you get comfortable with using the different relationships for these special right triangles, you'll be able to move quickly as well. Okay, number 10. Number 10, they're giving us across from the 60-degree angle, so 9 root 3. So I'm going to divide that by the square root of 3 to find this x, which is across from the 30-degree angle, which is 9. And then the hypotenuse is double that, which is going to be 18. All right, let's go to the next section. All right, so maybe a little bit more tricky here. So in 11 and 12, it says to solve for the variables, and if necessary, leave your answer as a simplified radical. You'll notice none of these are triangles, right? These quadrilaterals. So what I'm going to do is I'm going to draw something that we drew back in the first semester called an altitude, which is going to go from a vertex, and it's going to intersect the side across from that vertex to create a right angle, or essentially intersect perpendicularly. So I'm going to take this and draw my altitude. And when I do that, it's going to create a right angle right here. Okay? Now, if it creates a right angle there, then on the other side of that green line is also a 90-degree angle. And I know I can't make the 60 any smaller, but if that's 90 and that's 60, then this little tiny angle here is going to be 30. So we've created a 30, 60, 90 right triangle by drawing that altitude. You can also notice that we've got 30 inches right here. This whole thing on the side is 45, but after I drew that from the end of that 30, that means this is going to be 15 inches for that side across from the 30 degrees. So I know it's kind of hard to see, but that 15 inches is across from the 30 degrees, okay? So then to find this value for k, I need to find this right here, which is going to be the same as k, and that is across from the 60-degree angle, right? So using that relationship of the 30, 60, 90 special right triangle, that k is going to be 15 inches times the square root of 3. So k is going to be 15 root 3 inches. All right, I know it's a little tricky because that 60 is so big, but ultimately, hopefully you see that we went across from that to find that missing value. Okay, let me go to number 12. All right, number 12, I'm going to do the same type of thing. I'm going to draw an altitude from that part of it to intersect to make a right angle, right? So these are right angles here. And you can see we have 45 degrees in this angle, so that means up here is also going to be 45 degrees. And they're giving us this 3 root 2 as the hypotenuse. So each of these sides of this right triangle that I've created are going to be 3 root 2 divided by root 2. So they're each going to be 3 units. So that tells me that x is going to be 3. Okay, and then if I need this part here, this whole part here is going to be 4 from up there. Then y, which is that whole side, is going to be 3 units plus those 4 units. So y is equal to 7. Okay, let's go to the last page. All right, 13 and 14, same instructions for this one here. Okay, so 13. Now I've got 2 right triangles, and I'm trying to find x and y. And it's going to be tempting to do this, guys, but please watch out for this, is that you cannot assume that things are 30, 60, 90, or 45, 45, 90 unless somehow you know that they are, right? So I do see right angles to see that these are right triangles, but I can't assume that I can use those special right triangles. So what I'm going to do first is solve for x, because when I look at that right triangle, I have the hypotenuse, which is 7. I have one of the legs, which is 2, so I can solve for this other leg, x. So I'm going to do x squared plus 2 squared equals 7 squared using the Pythagorean theorem from our 9.1 lesson. So it's going to be x squared plus 4 equals 49. Subtract the 4 and you get 45. So taking the square root of both sides is going to give me x equals, let's see, that's going to be 3 root 5, right? 9 times 5 is 45, so 3 root 5. Now, we'll talk about this in class, but when you move into algebra, you're going to need to make sure you put plus or minus when you do those square roots of both sides, like in your work. The reason I'm not doing the plus or minus here is because we've told you guys that we want our side lengths and our angle measures to be positive only. So I did not include the plus or minus symbol that I will include if I have you in Algebra 2 next year. Okay, so we have found x. Now we can also find y. If we know that x is the hypotenuse of this other right triangle, I can do y squared plus 5 squared equals 3 root 5 squared. So that's y squared plus 25. All right, now we actually already have this number. I want to show you how you can square this 3 root 5. I'll show you right here. When you have 3 root 5 squared, the number out front is going to square, right? So this 3 gets raised to the second power, which is 9. But also the square root of 5 gets squared. So the way I think of it is the square root of 5 squared. But those are inverses of each other in terms of the operations. The square is going to make that square root go away. So it's just going to be 9 times 5, which shouldn't surprise you since we actually had that 45 in the problem or in the work to the left. Move the 25 over. With subtraction, you get 20. Take the square root of both sides. Again, we're going to just do the positive value. So y equals, and if I think about factors of 20, 4 times 5, and 4 is perfect. So 2 root 5 for y. So there's x and y. Okay, let's do 14. Okay, now 14 for this one. All right, I know it doesn't say the 30, 60, 90, 45, 45, 90. So again, don't just assume that it does, right? I can't assume based on how something's drawn that it's going to be one of those special right triangles. However, I do know it's a right triangle, and I have 2 of the 3 sides. So I'm going to use Pythagorean theorem to find that value for x. So I'm going to square 2 root 3 and 4 root 3, add those together, and that will equal x squared. So just like we did in that green version of 3 root 5 when we squared it, I'm going to do the same thing here. So 2 squared is 4, times the square root of 3 squared, which is just 3, plus 4 squared, which is 16, times the square root of 3 squared, which is just 3, equals x squared. So that's 12 plus 48 equals x squared. That's going to be 60 equals x squared. Take the square root of both sides. And I get x equals, think about your factors of 60. If you need to do the factor tree, please, please, please do the factor tree. Take that time. I know 15 times 4 is 60, so that's going to be 2 root 15 for my value for x. All right, let's go to these last 3. All right, where they're asking us to sketch a picture and then solve. We will, again, use simplified radicals. That's totally fine. So we want to find the length of an altitude of an equilateral triangle. So let's go ahead and draw an equilateral triangle. All right, and it says the sides are 8 centimeters. So 8 centimeters, 8 centimeters, 8 centimeters. Okay. Then it says we're trying to find that altitude, so I'm going to draw that altitude right there, which makes that right angle here. Okay, so we're trying to find that. Now, when you do this, all right, because that altitude is drawn to be perpendicular to the opposite side, it creates, this is now 4 centimeters right here, all right? And so what I can do is I can also remember that with equilateral triangles, they're all 60 degrees, right? So these are both 60, and that one up there is 60, but it's cut in half, so that means this is going to be 30, and that's going to be 30, so I have a 30, 60, 90 right triangle. So that means the altitude, which is across from the 60 degrees, is going to be that small one, that 4 centimeters, times the square root of 3. So this is going to be 4 root 3. So I'm going to say the altitude is equal to 4 root 3 centimeters. All right. Okay, so that's it for 15. Let's move on to 16. Find the length of a leg of an isosceles right triangle whose hypotenuse has a length of 6 root 2 inches. Okay, so I'm going to draw an isosceles right triangle. So here's the right triangle. And isosceles means these are the same. So this is a 45 degree, 45 degree, 90 degree right triangle. And it says the hypotenuse has a length of 6 root 2 inches. I'm trying to find the length of a leg, so I can use my notes from the very beginning that if I take that 6 root 2 and divide by root 2, I will get the value for each leg, which is going to be 6 inches. So the leg is equal to 6 inches. Okay, and finally the last one, number 17. Find the length of a side of an equilateral triangle whose altitude has a length of 6 root 3 units. So draw that equilateral triangle again. Okay, draw the altitude again. Creates the right angles. All right, this time it doesn't tell us the sides, but I'm going to fill in the angles, right? Equilateral triangles have 60 degrees here for each of those. And this one is 30. This one is 30. And then this altitude is 6 root 3 units. So if that is across from the 60, then I'm going to find the length that's across from the 30 degrees, which is going to be 6 root 3 divided by the square root of 3, which is just 6 units. And then to find the hypotenuse for this 30, 60, 90, you double that to get 12. So the length of one side of an equilateral triangle whose altitude has a length of 6 root 3 units is going to be 12 units. So length of side is 12 units. All right, guys, and that's it for this one. Check out the homework. Come see us for office hours, and good luck.